Hello and welcome to our third Thursday webinar. I am Tom Sandri, and today we are going to be talking about exploring the world of power factor and dissipation factor. Now, as many of you may be wondering, I'm sporting a new look this month. Well, let me just say, July summer, Texas, every little bit helps in trying to keep cool and comfortable dealing with the long, hot Texas summer. All right, without further ado, let's get on to our webinar. Now, most electrical equipment failures are the result of insulation deterioration. Power factor or dissipation factor testing is the most effective and common way to detect inefficient electrical equipment insulation. This test enables technicians to detect equipment insulation problems without making any internal visual inspection. Technicians that can properly perform and evaluate the results of a power factor or dissipation factor test can predict and prevent the failure of medium and high voltage transformers, circuit breakers, bushings, reclosers, switches, cables, lightning arresters, liquid insulation, potheads, rotating machines, and voltage regulators, just to mention some of the apparatus. The intention of this webinar is to guide the operator in the appropriate method of making capacitance, dissipation factor, or power factor measurements on power apparatus and to assist in the interpretation of test results that are obtained. Now, most failures of electrical equipment are the result of a breakdown in the insulation system. Power factor testing is an effective way to detect defective electrical equipment insulation. Power factor is the ratio of the capacitive or the charging current, measured in voltamperes, to the resistive or leakage current, which is measured in watts. It is a means of measuring insulation integrity, since the smaller the power factor, the better or the more efficient the insulator. Insulation may be deteriorating, however, the equipment may not fail for some time. Although this condition represents a serious hazard, if deteriorated insulation is detected before failure, it can often be reconditioned instead of being replaced. This allows corrective action to be taken during a planned outage before extensive equipment damage results from insulation failure. Power factor testing also makes it possible to detect equipment insulation problems without making an internal visual inspection. The result is a significant decrease in maintenance costs and downtime. Power factor testing is one of the best testing techniques for predictive and preventative maintenance. Power factor tests can detect the presence of poor insulation, even if there is a layer of good insulation in series. However, DC tests usually show a high insulation resistance under this condition. At a given voltage, the charging current and the dielectric loss increase as the quantity of insulation increases. However, the ratio power factor remains the same no matter how much insulation is present. This makes it possible to establish simplified test values for types of insulation. Power factor testing provides a measure and evaluation of the overall condition of medium and high voltage AC apparatus insulation under simulated normal frequency operating conditions. This is independent of the duration of the test. DC tests do not simulate normal insulation operating conditions. Furthermore, the results are affected by the duration of the test. Power factor tests provide a benchmark which may be compared over periods of time in an organized manner and are used to identify any trends on apparatus insulation. It provides a more complete picture of overall insulation conditions. Used in conjunction with capacitance measurements, it provides comprehensive data of the nature of the insulation. Now, dielectric material refers to the non-conductors or insulators in which an electric field can be sustained with a minimum dissipation of power. Unlike metals, no electricity flows in dielectrics when they are placed in an electric field. Instead, dielectric polarization occurs. Now, when a dielectric is placed in an electric field, electric charges do not flow through the material as they do in a conductor, but only slightly shift from their average equilibrium positions, causing dielectric polarization. This produces an internal electric field, reducing the overall electric field of the dielectric. Now, an important consideration for a dielectric material is its ability to support an electrostatic field while dissipating minimal energy in the form of heat. This dissipated heat or energy loss is known as the dielectric loss. The lower the dielectric loss, the more efficient or effective the substance is as a dielectric material. Another consideration is the dielectric constant, which is the extent to which a substance concentrates the electrostatic lines of flux. Substances with a low dielectric constant include a perfect vacuum, dry air, and most pure dry gases, such as helium and nitrogen. Materials with moderate dielectric constants include ceramics, distilled water, paper, mica, polyethylene, and glass. Metal oxides, in general, have high dielectric constants. So, a dielectric versus insulators. Dielectrics can develop an internal electric field which nullifies the externally applied voltage. Insulators do not develop an internal electric field. Dielectrics are easily polarized and can store charges. Insulators actively obstruct electricity. Dielectrics contain relatively weak bonds within atoms. Insulators contain strong covalent bonds. Dielectrics are mainly used in capacitors, power cables, transformers, and resonator oscillators. Insulators are used in high-voltage line systems and electrical appliances to prevent users from getting electric shocks. Insulation systems associated with many types of high-voltage power apparatus and devices often consist of a mix of non-homogeneous component parts. As such, a complete and highly accurate schematic representation of an apparatus insulation system may be quite complex and difficult to compose, perhaps consisting of a number of resistor and capacitor elements arranged in many varied ways. For discussion and analysis, it is convenient to represent an insulation specimen by a single capacitor combined with a single resistor. In this webinar, a specimen is usually considered as an entity which cannot be subdivided further for test purposes. The capacitor element represents the specimen's fundamental capacitance, for example, its ability to store electrically separated charges, while the resistor element represents the dissipated loss in the insulation when voltage is applied. As in this slide, there are two possible ways to combine a capacitor with a resistor. Now let's talk a little bit about a capacitor. Okay, two conducting plates with an area A separated by a dielectric with a thickness of D and a dielectric constant epsilon are basically the components of capacitance. The mathematical representation is capacitance equals area times the dielectric constant divided by 4 pi times the distance between the plates. Now, Michael Faraday discovered that when the plates between a capacitor were filled with an insulating material other than a vacuum, the capacitance would change. Dielectric constant is the ratio of the capacitance of a capacitor using that material as a dielectric compared to a similar capacitor that has vacuum as its dielectric. The dielectric constant of a vacuum is 1. All other dielectric constants are referenced to this standard. Now, here in the illustration, we see that the plate area, fixed distance, but in our first model, we use vacuum as the dielectric, and this would calculate out to 10 picofarads in this example. By substituting the vacuum with oil as the new dielectric, we see that with the higher dielectric constant, the capacitance increases and now calculates out to 22 picofarad. Now, here is a table that shows some common dielectric constants. Once again, vacuum, by definition, is 1. Air is virtually the same. We see that polyethylene, or XLPE, would have a dielectric constant of 2.25, paper, 2, mica, 5.4, porcelain, 7, oil, 2.2, and water at 20 degrees Celsius would have a dielectric constant of 80. So, let's go a little bit deeper into this. Given the 3 dielectrics that are in series, the dielectric constant, or epsilon, is 1 over 2.1 plus 1 over the dielectric constant of porcelain, 7, plus 1 over the dielectric constant of paper, 2, which equals 1 over the total, or 0.894. If we were to substitute and replace the oil with air, when we add up our dielectric constants, we see that the dielectric constant has now dropped to 0.609. And as a result, the capacitance of this specimen goes down. With less capacitance, there is less total current because there's going to be less capacitive current. So, let's bring this a little bit more into applicational practice. The hot collar test is a part of the procedure in the power factor testing of a bushing. When the power factor is done on a transformer, the test connections are on the transformer bushings, and the power factor test includes the transformer winding and the bushing. In order to measure only the power factor of the bushing, we put a circular ring which acts as a conductor around the bushing, a hot collar, which we connect to one side of the tester and the other side to the top of the bushing. In this manner, we can measure the power factor, capacitance, and leakage current of only the bushing. So, what conclusions can we draw from the following test example that we're going to illustrate. We're going to make 3 sets of measurements starting at the top of the bushing, working our way down, and the results are going to be as shown. So, at the top of the bushing, we're going to record our leakage current for bushing H1, bushing H2, and bushing H3. Now, working our way down, we go to mid-bushing. Once again, we capture our leakage currents on all 3. And then finally, we go to the lower or the base of the bushing. And once again, we take 3 measurements, H1, H2, and H3. And we render the results that you see on your screen right now. All right. Take a moment, look this over, and in the questions function, go ahead and type in what conclusion can we draw from these test results. All right, and the conclusion that we can draw is the oil level in the H3 bushing is probably somewhere between the locations used for hot collar test number 2 and hot collar test number 3. Again, toward the top of the bushing, the oil probably is being replaced by air, and hence that's why we're seeing a drop in the capacitance resulting in a drop of the total current due to a drop in the capacitive charging current. All right, let's talk a little bit more about dielectric loss. Dielectric loss is the time rate at which electric energy is transformed into heat in a dielectric when it is subjected to an electric field. The heat generated is given in terms of watts. Dielectric loss quantifies a dielectric material's inherent dissipation of electromagnetic energy. Example, heat. It can be parameterized in terms of either the loss angle, delta, or the corresponding loss tangent of the angle delta, or tan delta. Both refer to the phasor in the complex plane whose real and imaginary parts are the resistive or the loss component of an electromagnetic field and its reactive or the lossless counterpart. A dissipation factor or power factor measurement circuitry commonly views the specimen under test as a parallel capacitor resistor network. The equivalent circuit is repeated here, showing the various parameters of test current with respect to the applied voltage. V is the test voltage. I sub T is the specimen's total current. I sub C is just the capacitive or quadrature of the total current. I sub R is the resistive or in-phase loss component of the total current. C sub P is the equivalent parallel capacitance of the insulation specimen, and R sub P is the equivalent parallel resistance of the insulation specimen. The resistor element of the equivalent dielectric circuit shown represents the watt loss dissipated in the insulation when a voltage is being applied. R sub P represents that which is generally considered undesirable in a dielectric. It should be recognized that a certain amount of measurable loss is normal for most dielectrics, and therefore the existence of loss per se does not necessarily suggest an operating hazard. All right, now let's just review the properties of a perfect capacitor. Okay, in a perfect capacitor, we do not pass any DC current. Instead, the current leads the voltage by exactly 90 degrees. And the total current that would be measured would be all capacitive charging current. In the case of a perfect resistor, the current is always in phase with the voltage, and the total current would be all of the loss component or the resistive current. Now, in an ideal insulation system connected to an alternating voltage source, the capacitive current, I sub C, and the voltage are in perfect quadrature with the current leading. In addition to the capacitive current, there appears in practice a loss current, or the I sub R, in phase with the voltage as shown in this slide. The current taken by an ideal insulation, assuming no losses, I sub R would equal 0, is a pure capacitive current leading the voltage by 90 degrees, or theta would equal 90 degrees. In practice, no insulation is perfect, but has a certain amount of loss, and the total current, I, leads the voltage by a phase angle theta, where theta is something less than 90 degrees. It is more convenient to use the dielectric loss angle delta, where delta would equal 90 degrees minus theta. For low power factor insulation, I sub C and I are substantially of the same magnitude, since the loss component I sub R is very small. Now, mathematical representations. Power factor is defined as cosine times theta, which also equals sine of delta, which equals the resistive current divided by the current or total current. Dissipation factor is defined as the cotangent of theta, which equals the tangent of delta, which equals the resistive current divided by the capacitive current. Now, how is that for a flashback to your trigonometry training? All right, now let's start talking about test modes and configurations of the test equipment when we perform power factor or dissipation factor tests. To help us in understanding the operation of the test set, it is important to consider the relative positions of the test set's power source. Example, the 10,000 volt winding of the set's high voltage transformer, the measuring circuit, and the specimen being tested with respect to the test ground and the low voltage measurement leads. Power factor tests can utilize two low voltage leads and a ground lead simultaneously. We're going to use the Doble M4100 as our base model, but keep in mind, most power factor test sets or dissipation factor test sets will operate in this same manner. Now, couple notes. Basic laws of electricity. A difference in potential must exist between 2 points in order for current to flow. Current always returns to its source. Current always takes the path of least resistance, but current is on each path. All right, so let's start going into test modes and configurations of the test equipment. Kirchhoff's current law states that all current leaving must return. Therefore, all current leaving the test set through the high voltage lead must return to the unit, either through the low voltage test leads, the red or blue lead, or the ground lead. Internal to the test set, the test leads are connected to either the meter or metering circuit or to the guard. Test leads connected to the meter will be measured, and test leads that are connected to the guard will not be measured. By specifying a test mode, the user can choose to measure the red lead, the blue lead, the ground lead, or any combination, any two or all three. Test modes are selected in the Doble Test Assistant field software, or DTAF software, and instructs the test set which test leads connect to the meter and which test lead ports are going to connect to the guard circuit. So here's our high voltage input, our measurement inputs for both the blue channel and the red, and moving on to our first test mode, a grounded specimen test, GST. Here is going to be GST, ground, red, blue. With the analyzer in the GST, ground, red, blue, the low voltage leads are brought to ground potential. Thus, the low voltage leads may be used to connect ground to a specimen terminal. Now, in a GST test, as we see, ground is always going to be measured. In this situation, since ground is measured along with red and blue channel, all three paths are being measured. And our measurement is going to be that of current I sub A, current I sub B, and current I sub C. Now, in a grounded specimen test, GST, guard, red, and blue. So again, in a GST test, ground is always being measured, as we see here, going through the metering circuit, but we're going to guard and not measure the currents flowing on the red and the blue channel. So the result of our measurement would be only the measurement of current I sub C. All right, a grounded specimen test, once again, ground being measured since it's a GST, but we're going to guard red and we're going to ground blue. Now remember, by grounding blue, that means blue channel will be measured. By guarding red, that will not get connected to the metering circuit and will not be measured. So the result of this test would be the measurement of current I sub B plus the current I sub C. Okay, now we're going to do a GST. We're going to guard, not measure the blue channel, and we're going to ground, and since it's a GST measurement, grounding means we're going to measure the red channel along with ground, as we see in this diagram. The result would be the measurement of current I sub A plus current I sub C. And since we're guarding B, we do not measure current I sub B. All right, along with the GST tests, we also have what are known as ungrounded specimen tests, or UST. In ungrounded specimen tests, ground is always guarded. Or another way of saying this is ground is never measured in a UST configuration. So here we have UST. We are going to guard everything coming in on ground, and we're going to measure everything coming in on the red and blue lead. And thus, the test set results would be the measurement of I sub A plus I sub B. Our next configuration of a UST would be unshielded specimen test, we're going to measure the blue and we're going to ground red. Now remember, in a UST test, when we say ground something, effectively we are not going to measure it. It is going to be guarded, because remember, in a UST, ground is not measured. So in this configuration, since we're measuring B and we're guarding the ground channel and the red channel, we are only measuring current I sub B. Now, here's a summary of the various test modes and the connections that you would have associated with power factor or dissipation factor testing. Here we show the various UST or unshielded specimen tests, as well as the GST and the grounded specimen tests. So ungrounded specimen tests and grounded specimen tests, and the various lead configurations. So, why so many test modes? Well, let's give again a practical example. Let's look at a two-winding transformer. Now, looking internal to that two-winding transformer, when setting up the test, we basically short out the high voltage windings and the low voltage windings. The result is we basically now create a capacitance between the high windings and the low windings, and we have a capacitance from the high windings to ground and to the low windings to ground. Or in essence, we configure a circuit like this. We have capacitance high to low, capacitance high to ground, capacitance low to ground. So in this complicated insulating system, we're going to see how the various test modes allow us to isolate, troubleshoot, and try to determine where the insulation failure or breakdown is occurring. So starting with our GST ground. So here, everything is being measured since it is a grounded specimen test. So we are applying potential to the high voltage leads, which is causing a current to flow between high and low, a current which is flowing from high to ground. The insulation measurement is going to be the combination of the capacitance of high to ground and the capacitance of high to low. That is the section of the insulating system that we are in essence measuring. Now, our next example is going to be a grounded specimen test where we're going to guard the red and the blue channel. So here we see the current flow in red going from high to ground, and we see the current that is coming up through the red channel, which is the high to low current, that is going to be guarded. The result is we have now isolated and we are only measuring the insulation contribution of the capacitance of high to ground. Now, looking at our ungrounded specimen tests, we are going to do an example of UST measuring red. So again, we apply our potential. The current that flows from the high windings to the low windings gets picked up on the red channel. That is being measured. The current that is flowing from the high windings to ground is being picked up on the ground lead. And remember, in a UST measurement, ground is always guarded or not measured. The result is we are measuring simply the insulation or the component of insulation between the high and low windings. Now, in a GST ground, we are applying, in this model, similar to when we applied the potential to the high side, except notice here in the slide we are now applying the potential to the low side. So in essence, we are now measuring the current going from low to high and the current flowing from low to ground. In essence, we've isolated this section of the complex insulation, the capacitance of low to ground plus the capacitance of high to low, or technically speaking, low to high. All right, in our GST, we're going to guard the red channel. So here, we are applied to the low side bushings. We're going to measure the current going from low to ground, and we are going to guard everything that is coming up the high bushings feeding back on the red channel. So we've isolated, and we're now only measuring the low to ground insulation properties. Next, we're going to do an ungrounded specimen test and measure red. Once again, voltage being applied to the low side. And the result is we are measuring the insulation property or capacitance of low to high. All right, so once again, why so many test modes? Well, let's take another example. Let's take a look at a 6-terminal motor stator. So in this configuration, effectively we've got 3 windings. We've got capacitance from the A winding to ground, B winding to ground, C winding to ground. We have capacitance from the C to B, the A to B, capacitance from winding B to C, and also capacitance from winding C to A. A slightly more complex insulating system. And here would be the equivalent circuit. So again, in trying to troubleshoot or isolate where the insulation breakdown may be occurring, here's where the various test modes and configurations are going to help us isolate. So once again, in a grounded specimen test measuring ground, we're going to short out all the windings. We're going to connect to ground. Our measurement lead will be placed on the B winding. Our blue lead, measurement lead, will be placed on the C winding. And we are going to energize on the A winding. The result would be we are measuring the capacitance of A to ground times the sum of the capacitance A to B plus the capacitance A to C, as we show in the current flow diagram. Now, in an ungrounded specimen test where we measure R, once again applying the voltage to the A winding, the result of this measurement would be isolating and looking at only the capacitance of A to B. Working our way through, we're going to do a GST ground again, but this time we're going to energize on the B winding. Our red lead will be placed on the C winding and our blue lead on the A winding. And here we can see the current flow. And we would be measuring the capacitance of B to G times the sum of capacitance B to C plus capacitance of B to A, or in our circuit diagram, this combination of insulation. In an ungrounded specimen test measuring on red, once again we're energizing on the B winding. Here's our current flow. Yellow is guarded and not measured, red is actually measured, and the result would be we have isolated and we're now measuring just the capacitance or insulation properties of of B to C. Next, we'll go on to a grounded specimen test. Here, we're going to energize on C. Our measurement leads are going to be placed on windings A and B, and obviously ground. We energize, and in essence, we've isolated, and now we're measuring the combination of the capacitance of C to G times the sum of the capacitance of C to A plus the capacitance of C to B, or this various sector of the insulation. In our ungrounded specimen test measuring red, again, we're now going to apply onto the C winding. What is shown in yellow dashed lines is being guarded or not measured. What is shown in red dashed lines is the current flow that is going to be measured coming through the red channel. And in essence, we've isolated and we're now only measuring the capacitance of A to C in our complex insulating system. All right, now let's jump into interpretation of measurements. Here we see the NETA table 100.3, maintenance test values, recommended dissipation factor or power factor at 20 degrees Celsius for liquid-filled transformers, regulators, and reactors. Now remember, in all NETA literature, in the absence of consensus standards dealing with transformer dissipation or power factor values, the NETA Standards Review Council suggests the above represented values. Maximum values for oil are based on data from the Doble Engineering Company. All right, let's talk a little bit more about interpretation of results, a general analysis. We want to compare to nameplate data. We want to compare to previous tests and establish changes or trends. We want to compare our measurements among the various phases of a transformer. We want to review not only percent power factor, but we also want to take a look at the current, the watts, and the capacitance as well. Percent power factor that is much lower than expected is just as unacceptable as that which is much higher than expected. A change in current or capacitance of 5% or more is a cause of concern. Now, let's also take a look at negative power factor values. They do occur from time to time. Creep currents inside an insulation system, or more commonly on surfaces, create change of potential distribution that may give increase or decrease dissipation factor, and in some cases also negative dissipation factor. This condition is most likely to arise when making ungrounded specimen tests and grounded specimen test measurements on specimens who have a capacitance value of a few hundred picofarad or less. Equipment such as bushings, circuit breakers, and low loss surge arresters will fall into this category. The error is usually accentuated if tests are made under unfavorable weather conditions, especially a high relative humidity, which increases surface leakage. There appears to be no clear-cut way of knowing whether an error is significant or what remedies should be taken to overcome an error. A frequency sweep may give additional information. The best advice is to avoid making measurements on equipment in locations where negative dissipation factors are known to present a problem when unfavorable weather conditions exist, especially high relative humidity. Okay, good statement, but in practice, we all know the outage is scheduled when the outage is scheduled, and the client expects us to perform miracles. All right. So make sure the surfaces of porcelain bushings are clean and dry getting tongue-tied here. Make sure the surfaces of porcelain bushings are clean and dry to minimize the effects of surface leakage. Make sure all items such as wooden ladders or nylon ropes are removed from the equipment to be tested and are brought out of any electrostatic interference fields that could influence your measurements. And that concludes our webinar today on power factor and dissipation factor tests. As always, thank you so much for your attention. Thank you so much for taking time out of your busy days. For those that are watching from overseas, various countries, various time zones, thank you for giving up your mornings, your late night evenings, and again, thank you all for giving up the time in your busy schedules to attend our Third Thursday webinars. As I always say, Matt and I really enjoy this program. We love doing these webinars for you, and we do truly hope that you are getting value in the series. So, without further ado, how about if we just get to those questions and answers?